That is weird. And
Did not feel well.
It was
and
not
then-
perfect.
Oh, no.
and no guys. I was like, wait a second. Like the women outnumber the guys in this class to begin with, but there's none. All right. Okay, chapter 7. Fun. So 7.1 is literally looking at two different things and determining which one they are, because the rest of chapter 7 only deals with discrete random variables. Yay, we got a guy.
Wait, am I not the only one that's late?
No, you're not the only one that's late, but you're also the only guy that came in. And I was like, I was literally the only one in the room. So chapter 7 deals with discrete random variables, and chapter 8 deals with continuous random variables. So they are very different in how we want to treat them. Okay, so chapter 7, section 7.1 literally determines like what's the difference between them. All right. So a discrete random variable is countable, and you can list all the possible outcomes. Okay. So a discrete random variable is a countable number of possible outcomes. So you should be able to list or come up with a count of exactly how many options there are or outcomes there are. So a deck of playing cards is a discrete random variable because I know exactly how many of them that I have. Okay. More is showing up. Very good. All right. So we'll talk about it in a minute. So what would be the difference between a discrete random variable and a continuous random variable? Yeah, anything. Like literally, like, because I can have decimals that are discrete, but continuous is the entire spectrum. So all the numbers from 1 to 2, every number in between those would actually count. Okay, so a continuous variable is every possible combination with it. It can be from 1 to 10. It doesn't necessarily have to be an infinite number of values, but even between 1 and 10, there's a ton of different values in there. So that would be a continuous random variable. So discrete and continuous. Let's look at a few of them. Yes.
Can you give a quick, simple definition just so I got to write down real quick?
Of what?
Discrete and
Discrete's right there. It's a random variable which is countable number of possible outcomes. So you should be able to list or state exactly how many outcomes there are. And continuous, since I'll just flip over to this one, can assume any value on a continuous segment of random number. So basically any number between 1 and 10. That's continuous. If I said only integers, so it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, that would be discrete. Does that make sense? The difference between the two? Okay. All right, let's look at a couple examples. I just did those two. All right, so if we're tossing a die, is that discrete or continuous?
that would be discrete because it has a countable number of outcomes.
Correct.
It calls me like 1 through 6.
Yeah, or 1 through 6, 1 through 12, whatever it happens to be. So yes, if it doesn't say otherwise, we'll assume 1 through 6. Okay, so if it is discrete, we can list 3 things about it. We can state the variable. We can list all possible values of that variable. And we should be able to determine the probabilities of these values. Okay. Now, some are going to be easier than others to do number 3. Number 2, we should be able to do. So in this case, what is the variable? No, it's actually the outcome of the roll. Because if it was actually the number of rolls, that would actually go on forever in that case. So, but it's the outcome of the roll. So like if I roll the die and it comes up with a 3, that's the variable. So my variable is the outcome of the roll. what are the values that I can have for it? In this case, it's 1, 2, 3, 4, 5, and 6. Or you can say the integers between 1 and 6. Everybody know what integer is? Okay, good.
All numbers.
Yes.
And you,
Integers can technically be negative, where whole numbers have to be positive. That's really the only difference between the two. All right. What is the probability of each outcome? So what's the probability of me getting a 1? Yes. What's the probability of me getting a 2? What's the probability of me getting 3, 4, 5, and 6? That is known as a probability distribution. Okay? It's listing every outcome, and it's listing the probability of every outcome. Okay. All right.
oh, you said the
Yep.
thing for the discrete random variable is variable value and probability, right?
Yes. You should be able to come up with the variable. You should be able to tell me what the values are. Anytime it's discrete, you should be able to tell me what the values are. It might be, like I said, a statement of them. It might not be listing every single possible outcome if there's too many to list, but you should be able to state what they are. And you should be able to come up with a probability distribution if it's known, which, like the next one I'm going to show you, is kind of along those lines. All right. So the head nurse of a pediatric division of the Sisters of Mercy Hospital is trying to determine the capacity requirements for the nursery. She realizes the numbers of babies born at a hospital each day is a random variable. She will have to develop a description of the randomness in order to develop her plan. So, step 1, is this a discrete random variable or a continuous random variable? Yes.
I would say it's a continuous because there's not really a number of like how many set babies are produced out of like 1 out of like 10. It's something that can kind of increase or decrease depending on the day.
Okay.
They kind of assume a number of babies mathematically.
Okay. Yes.
You can't put a natural process on the clock. You can't tell someone, oh, you have this kid now, this kid now, this kid now, so it's continuous, because you can't necessarily reach every
Okay.
single day.
Let me take let's take a step back because we can do this for either one of them. What's the variable? What is the variable I'm looking at? What was it? Huh? And what's the capacity requirements based on?
How many babies?
How many babies are born? So the variable I'm looking at is how many babies are born, right? Okay, so X is the number of babies. Okay, that's my variable. So both people have stated it's continuous. What is the difference between continuous and discrete? Yes.
Wouldn't it be discrete?
That's not what I asked right now. Give me a second. What's the difference between discrete and continuous? I can count all the outcomes, right? And continuous is? No. Continuous is every value between values. So, right. Can I have a half a baby?
That's not gonna be very discrete.
It is still a baby. Unless it's dead and then it's not a baby. But even if it's born and it's alive, if it doesn't have legs, it is still a baby, not a half a baby. So, we cannot have a half a baby. So, therefore, I didn't make up the problem. Therefore, it is discrete. That's honestly, we talked about this before, actually, with some other things we were looking at variables at the beginning. The difference between discrete and continuous is basically, can you have half of something? Okay. And even if it comes out to be a decimal, it's like, can you have half of that? Like, you should be a continuous, that would all work. Okay. So this is a discrete variable. Now, the next thing we should be able to state is, what are the values that I would come up with? In this case, the values would be basically any whole number. Okay. So my values, I'm not going to list all the values, but it could be any number from, let me actually spell these correctly, from 0 to anything. Yes.
So for a continuous number, it would have to be continuous random variable. It would have to be like some kind of decimal for it to be qualified as that.
It doesn't necessarily have to be a decimal has to be able to be a possible answer. Okay. So there's debate about if money is continuous or discrete, but we're going to assume that at this point, money would be continuous. Money would be continuous. Like, you can have cents and everything else. And even at that, depending on if you're talking about interest, it can even go past cents. All right. So in that case, currency would be continuous value. Temperature. If I was looking at the temperature over the course of every day, over the course of a year, temperature is continuous. I can have 62.357 degrees. Okay. You're not going to sit there and look at them all out, but that's a possible value for temperature. Does that make sense? Temperature is not only 63, 64, 65, 66. Every number in between those would also work. Does that make sense? So that's the difference between those two. Now, would I be able to come up with a probability curve for this? Or a probability distribution for this? No. Because, as you said, we don't know how many babies are born every day, right? It could be anything. So in this case, we could, over time, develop what we think would happen. But based on the information they gave me here, I would not be able to come up with a probability distribution for it. That does not mean it's not discrete. It just means I can't come up with it for this situation. All right. Oh. Okay. Thank you.
I don't know what that sound was.
All right. So a local restaurant has an express policy that states that lunch will be served within 15 minutes of ordering, or it will be free. Obviously, the restaurant is not wanting to give away products, but the length of time to prepare each meal varies because of the difference in preparation times of each dish, load in the kitchen, blah, 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 blah. All right. Is this it actually says it there. Would this be continuous or discrete? This is continuous because time is continuous. Okay. So what is the variable we're measuring here? We're measuring the time from ordering. And my values would be what? Well, the time from ordering technically would be 0 to infinity because it could be at as much time as you want, right?
Could we go to 15 because at 15 then it'll be free?
Now, so the way this is where your variable and your values have to work together. So our variable is the time from order. Now, yes, after 15 minutes the order is free, but could the order come out in 20 minutes? Yeah. So the time from ordering, 20 minutes would still work. That would be a possible answer. So it would technically be 0 to whenever the restaurant closes or wherever the person gets totally sick of waiting. So there's no end value on it. But it's continuous because every value in there would make sense. Like I can have 15.35 seconds. Like that would make sense. So now, yes, the restaurant would want it between 0 and 15 minutes at all times because they never want to give anything away free, but that can happen. That's why Domino's got rid of the 30 minutes are free thing because they couldn't control all the variables in the delivery process. So they got rid of the 30 minutes are free guarantee. But now you can get an emergency pizza for no reason. All right. Let's look at a couple of ones real quick and just do these. Let's just go a little more for discrete and random or discrete continuous before I jump into calculations about discretes. All right. A, the number of emergency phone calls received per day by fire departments. Discrete or continuous? Why?
Because you get
Yeah, you can't have that. Speed of pitches in a major league pitcher. Discrete or continuous? Continuous, because speed can be continuous, right? The weight of a lobster caught in Maine. Continuous. Weight is continuous. The number of defective circuits on a computer chip.
screwed.
Discrete. I can't have half a defective part. The time it takes for a 5-year battery to die. Continuous. Time is continuous. Yes.
Would that be continuous? Because like we stuff like a year and like 2 days.
Yeah, that's still
Solid
continuous.
number two, there's 20.
Yeah, so time, yeah, because basically like anything, you could have a time 2 days or a year, 2 days, 3 hours, 5 minutes, and 15 seconds. Like even at that point, 15.25 seconds. So like time is continuous. Okay. Time, weight, speed, those things are all continuous values. All right. I think we got the concept of what discrete is and continuous is. Now, the rest of chapter 7 is literally only talking about discrete variables. We will talk about continuous when we get to chapter 8. All right. A discrete probability distribution, which we already looked at one. So the sum of all the probabilities must equal 1. And the probability of any value must be between 0 and 1 inclusively. So there could be a possibility of 0 and there could be a possibility of 1. However, the sum of them all must equal 1. So if we look back here, this was my probability distribution for a die, right? Does it meet the 2 criteria I just told you? Is the sum of all these 1? 1, 6 plus 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 1, 6 is 1. Okay. Are they all between 0 and 1? Yes, because 1/6 is 0.16667. I think that's 1/6. So yes, it is between 0 and 1. So it meets the 2 criteria for that. So that is a correct probability distribution. All right. Let's look at tossing a coin 3 times and counting the number of heads. So what are the variables? What's the variable in this case? The variable is the number of heads. Okay. What are the values for the number of heads that I can get?
Since you're tossing it 3 times, wouldn't it just be, or it could be 1, 2, 3, or 0?
Yes, 0, 1, 2, or 3. I can have no heads, I can have 1 head, I can have 2 heads, or I can have 3 heads. Those would be all the possible values, correct? Okay. All right. Let's make our tree chart so we can see our options. So we have heads, tails, heads, tails, heads, tails. Okay, so I have heads, 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 tails, heads, tails, heads, heads, tails, tails. Tails, heads, heads, tails, heads, tails, 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 heads, and tails, tails, tails. How many heads in the first one? 3. Well, the way I wrote it.
Oh.
And then there's 2 in that one, 2 in that one, 1 in that one, 2 in that one, 1 in that one, 1 in that one, and 0 in that one. Everybody understand where all that came from? Okay. All right. So, everybody got this down somewhere? Because we're going to use it in this one. What's the probability of me getting 1 head? Or no head, sorry. One out of 8. What's the probability of getting 1 head? 2 heads. 3 heads. Okay. Does that meet the criteria of a discrete probability distribution?
Yes.
For all the values between 0 and 1? If I add them all up, does it equal 1? Yes. That is the probability distribution of the number of heads observed. Okay. Notice this. Okay. So there's actually 2 different size x. The big X is telling you what the variable is. The little x would be the number. So this one right here would be P of x equals 0. That's P of x equals 1, P of x equals 2, and P of x equals 3.
What did you say?
The variable. So in this case, the variable is the number of heads. All right. Let's look at this one. So let's look at one that's not a simple flipping of a die or coin, things like that. So they gave us a frequency distribution. During the last year, it kept records of its computer sales for the last 200 days. They had 0 sales on 40 days, 1 sale on 20 days, 2 sales on 60 days, 3 sales on 40 days, and 4 sales on 40 days. What is the variable? No.
Sales?
Variable is sales. How many computers did these sell? Okay, so variable is sales in this case. What are the values that I can have? Right. 0, 1, 2, 3, 4. Now we can make our probability distribution. What's the probability that I had 0 sales? Already added 200. Do the division for you. We want this as a decimal. It's gonna be easier to do the rest of the calculations. 0.2. So 0.2. What's this look like? You've done this already. We did this on our last test. You got your frequency distribution. What was the next column over after frequency distribution? Relative frequency. So in essence, the same thing here.
In one of my classes, they do a frequency chart for our observations.
Yeah, how many times things happen?
I'm just making it.
Yep.
It's not necessarily. I don't necessarily need the classes.
But they do. That's kind of the point.
They do.
All right. The next one. One. What's the probability of 1 sale? 0.1. What's the probability of 2 sales? 0.3. And then the nice thing is we already did 40, so that's 0.2 and 0.2. All right. So, does it meet the 2 criteria? Are all the values between 0 and 1? Yes. Does the sum of them equal 1? Yes. Okay, so that has to happen, otherwise this doesn't work. All right. What's the probability that he'll sell at least 2 computers each day? So at least 2 would be 2, 3, 4, right? So that'd be 0.7. At most 2 per day. That'd be 0, 1, and 2. So that'd be 0.6. Okay.
So just adding the probabilities.
Yeah. That the way the questions were, yes, that's all they wanted you to do for that one. Now notice, if you add those 2, you do not get 1. Because at least 2 and at most 2 both include 2. Okay, so that's in both of those. So good. All right. So you take pictures and then it instantly goes into your thing so you can write on them?
Well, it doesn't go instantly.
It takes a second, but yeah.
I have to like crop it and stuff. And
Oh.
then transfer it over. But yeah, so I take pictures and I move it so I can like write on it and I don't have to write questions down.
It makes sense. All right. So now let's go just do a little bit of algebra. We're only very little. Don't worry, very little. You actually can create what's known as a probability distribution function. This would be an equation that would come up and give you the probability of each of the values. Okay. So in this one, we have the probability would be x squared divided by 30 if x was 1, 2, 3, and 4. And anywhere else it's 0. So I don't necessarily care what the variable is in this situation, but what are the values of the variable? I don't necessarily have to have the 0, but it's 1, 2, 3, 4. Those are the values that would work for this variable. So 1, 2, 3, and 4. So what is the probability of what? It'd be x squared divided by 30, right? What's 1 squared? 1, so it's 1 over 30. I'm not going to have you make these decimals because it's going to be a messy decimal, and I'm not really doing anything else with this. 2 squared is 4, so this would be 4 over 30. 3 squared is 9, so it'd be 9 over 30. 4 squared is 16, so it'd be 16 over 30.
That would just be the number squared.
Yeah. Are they all between 0 and 1? Does it add up to 1? Yeah, just add the numerators. As long as it is 30, you get 30 over 30. So yes, this is a probability distribution function. If it didn't add up to 1, it wouldn't be. Okay, so you can have an equation that comes out, but it just doesn't work. Like that, not every function is going to be a probability distribution function. Obviously, the one they created would work, but always have to ask those questions. Yes.
Okay, what would this be used?
This, I can't come up with an exact example off the top of my head. So, as I was talking to my pre-calc class, most of the situations where you guys are going to use this stuff, if it's an equation like this, is you're going to have a bunch of data that you then have to model something out of. So if we have a bunch of data and we plot it and we see some kind of shape for it, but we want to be able to predict what's going to happen in the future. The only way to predict what's going to happen in the future, a lot of times, is to create an equation that models that data. That's where something like this could come in. You could say, this is the model for the probability distribution. And now I can then use that to say, okay, what's going to happen if I have 50? I can then figure out what that piece is going to be because I know what the model is going to be for it. Does that make sense? So I can't give you an exact example because I don't honestly know one, but that's typically where these models and functions and stuff will come into play. All right. Yeah. All right. Expected value. Expected value helps you to determine what you would expect to earn given a certain amount of things. Or what would so in essence, expected value helps you kind of figure out what the average is of whatever's going to happen. So what is the odds of something going is those things going to happen? So to do that, we've got this crazy formula, but it's really not that insane. Basically, all you're going to do is take the probability of the event happening and multiply it by whatever that event is, and then add all those together. If you think, and when you look at what we're going to do, in essence, you are doing a weighted average, which we've talked about before. Remember, we did weighted averages? As long as the probability adds up to 1 or 100, if you're thinking about it as percentages, a weighted average is no different than your expected value. This is where you can figure out what your expected value is for like games. Okay. So let's look at an example. So these are 2 investments. I will let you take your picture before I move things around. All right, so these are 2 investments. Okay, so because I'm going to actually hide the word problem because we don't really need it. The question is what would be the expected value of option A, for example? So to do that, I'm actually going to put this over here, like this, so I can write next to it. Duplicate the slide before I write anything on it. All right. So we've got the probability, we've got the profit. We're going to multiply each of those together, and then we're going to add them up at the end. So it's negative 2,000 times 0.2. Actually, I think it's negative 400. I think you're off by a decimal. So this is x times p of x. 0 times 0.1 is 0. 1,000 times 0.3. 2,000 times 0.3. 4,000 times 0.1. Add them all together. Okay. So your expected value, if you invest in option A, would be a profit of $900. Okay. You could have a profit of negative $2,000. You could have a profit of $4,000. But if you do put enough money into this often enough, you should expect a value, an increase of at least $900 in the long term. All right. Let's look at option B. What's negative 3,000 times 0.2? Negative 1,000 times 0.1. 2,000 times 0.2. 3,000 times 0.3. And 4,000 times 0.2. Add them all up.
It could be
1,300.
okay.
You're off by one. 17, 21, 20. Yeah. No. You were right. 1,400. You were right. I was off. I was off by one. I literally just did it again. I'm like, no, wait, it was 1,400. All right. So probably, or option A was $900 expected value. Option B was $1,400. Okay. So in the long run, which investment would be a better option? Option B, because your expected value is higher. But that's in the long run. In option A, you could lose $2,000, but that's the only loss, right? The rest of them, you're either gaining or losing nothing. Option B, it's losing 3,000, losing 1,000, or making money. So there's more options of you losing money in option B than option A, but you're going to make more money as well. So, yes.
Just a question. Is this a list of what happens throughout time? Like you lose $200, but then you'll gain $2,000?
No, not necessarily.
Oh, this is like probability.
It's kind of like a game. Like every time you invest, you could have, this is one of the things that could happen.
Oh, stock market. Right?
Yeah. So we remember we've talked about roulette. The expected value of roulette is negative 0.526. Oh, sorry, negative 0.0526. That's the expected value of roulette. So that means every time you play $1 in roulette, you should expect to lose about 5 cents. Okay? You play it long enough, you're going to lose. It's inevitable. Does that mean every time they spin the wheel, you're going to lose? No, you can hit it big. But you play it long enough, that's where the expected value comes out to play. Okay? The more you play in the two options that we just did, you're going to make money. You're going to make more than option B than option A, but you got to put a lot more in to make that happen. In any casino game, your expected value is always negative. There's not a single casino game that your expected value is positive. Because if there was, it wouldn't be a casino game. Because they need to make money. That's called the house's edge. That's where the house makes their money. Okay? All right. Does expected value make sense? Okay. The other thing that we can do with it is just like we were doing before. We were talking about standard deviation of those things. We can find variance and standard deviation of them. So we can still do that on probabilities. And just like we were talking about before, we were looking at variance and standard deviation. Standard deviation tells me how things are spread, correct? So the more things that are spread, the more varied it would be. So if you were looking at A and B, I'm going to come back to that slide in 1 second. If you were looking at these two here, I actually have them here. Never mind. If you were looking at those two there, which one would you think would have a higher standard deviation? Option A or option B? Okay, because it's more spread, right? It's going from $3,000 down to $4,000 up, right? Yes.
I would also say B2 because the difference between each variable is a lot more smaller than in comparison to option A, where it was 2,000, 0, 1,000, 2,000, 4,000.
Yeah. All right, let's find out. So, remember when we did standard deviation originally, you had to take each of the values subtracted from the mean, square it, and do all that other wonderful stuff. Unfortunately, here you kind of have to do that. Because these are considered more weighted averages than just a list of numbers. So there's no way for you to just put the numbers in there and do this out. the nice thing is when we're doing these, you're not going to have many numbers to do. It's going to be little tables like this to do it in. Like anything other than this, we'd use a computer to do, like Excel to do most of the calculations for us. So the mean in this situation is my expected value. Because remember, we just talked about expected value. Expected value is kind of like that average. That's like that weighted average. So when we figure out our expected expected value, that is what's considered your mean. So for option A, our mean was what? $900. So my mean was 900. Okay. So we're going to use Desmos scientific calculator to do this. I know you can't see it. I'm going to switch over in a second. I just want the actual numbers. It was 0.2. Okay, so in Desmos, because we're going to use a calculator to do this to make our lives a little bit easier, take each of the values and you subtract your mean. Okay. Because we want to find the difference between it and the mean. So minus 900, because A was 900. And then square them all. This is where the nice thing of old Desmos comes into play, because you can literally just type them all in like this. And then multiply them times the probability. So it's the value, I know it's a lot of steps, minus the mean squared times the probability.
So value.
Value minus mean, or expected value, depending on how you want to remember it, squared
Squared
times the probability.
times probability.
Times the probability. So that's how I got negative 2,000 minus 900 squared times 0.2.
That's the standard deviation.
And this is going to figure out our this is how we figure out our standard deviation again. Variance is the same thing. It's just one less step. I'm going to actually show you both of them in a second. The only difference between variance and standard deviation was the square root. All right. Last step we have to do with this, add them all together. Well, one extra step. So we add them all together. And then the very last step is we take the absolute value, or the not the absolute, the square root of it. So my standard deviation for A is 1758.
When you added them together.
Add them together, and then take the square root of that. When you add them together, that's your variance, which we don't really use. The square root of that's their standard deviation. That's what typically we use. So add them all up and then take the square root of it. I know. I wish I had an easier way to do this. It's like, I don't.
I had to deal with another kid who broke skin through a shirt today.
God,
This is probably.
I'd run to deal with math. Yeah, I could never deal with like, somebody said, like, deal with Lucas. No.
Honestly, I love it though. Like, I love my class. It's not the worst. Like, even on their bad days, like today, I still come home like feeling like a ray sometimes. I'm like,
They're cute, but that's about it. It's like,
My
no.
class, so, like, I have some kids in my class who, like, I lovingly say I really beat them because they, I swear to you, they fought their way from hell. But, like, I love them anyway.
All right. So we found the standard deviation for A. Let's do B. So we thought B was the worst, was the better, or was more or wider spread. So let's find out. What was the? It was 1400, right? All right. What was the first value? Was 2000, right? I'll just type it all in again. What was the first value for the option B?
I do agree.
Negative 3000 minus 1400 squared. And what was the probability? I know she has it sitting in front of her. So
So many numbers written down here.
right? No, it's literally in the table.
Oh, on the table?
Yeah.
Oh, 22.
Thank you. Okay. So that's the first one.
One more. Make it 1,000.
Negative 1400 squared times 0.1. And then it was 2000. And 3000.
3.
And 4000. Okay. Add those numbers together and take the square root. I'm just going to do this all at once so I don't have to actually do the square root separately. You just do the square root over all of them. Three, 5, 2. Okay. And that standard deviation's 2,577. So option B, the expected value is higher, but it's more varied. So if you're looking for a good long-term investment, one that you're going to do long-term, option B might actually be a good option because it's going to get closer to that expected value. If you're looking at something more short-term, you want something that's not as varied. So you might want to stick with option A. Okay. That's the difference. I could be mean and tell you to figure this out for roulette. Do you know? So we look at the roulette table. You have all your numbers 0, 0, 0, 1 through 36. But depending on how, there's all the different bets in the middle too that you can play. And then you have red, black, you have even odd. So like, there's not just 38 options that you can play for it. So when you're doing like like to figure out the probability, you have to figure out all the probabilities of everyone. So it's a lot. That's why I said these are very short, simple little problems that you're going to have to work through and do. So notice the same stuff comes back. So we were talking about standard deviation and stuff like that when we were looking at values and we're looking at the bell curve and stuff. That stuff still comes into play when we're looking at probability distributions and those type of things. So, and actually, most of the time when you're dealing with things, you're going to be dealing with a probability of something occurring more than here's just the number of counts that you get. So this is the type of stuff that you typically will see more often in the real world type situations. All right, I'm done. That's 7-1 and 7-2. We'll do 7-3 and 7-4 on Thursday.